Now I would like to present you something extra for the final lecture, which is the virtual crack closure technique. Now recall that in the fracture mechanics slide, we have shown that during crack propagation, there is an energy balance between the release of strain energy and the creation of a surface of crack. In the virtual crack closure technique, there is another energy balance, which is equivalent to the previous one, which is that the energy to create the crack equals the energy to close it. So this is a very interesting idea. This technique is very popular in NASA, so I would like to add it, and it's also available in Abaqus. So I think it's useful for you to know about it. Here, based on this assumption, we can consider that just before the crack propagates from this point to this point, there is a certain force trying to close this crack. And if we zoom in, and we give a normal mode 1 direction and mode 2 direction respectively. So here, it assumes that, and the VCCT it assumes that the crack propagates in a self-similar manner, which means that if this crack tip were to open up, it is going to open up just by the same amount as before, which is the opening at a distance of dA behind the crack tip. So you can imagine in a self-similar crack, this whole region is going to shift to the right by a distance of dA. So we can then, based on this assumption, calculate the energy release. So the energy release in mode 1 and mode 2 can be calculated as a product of F1, Fi, which is a component of F along the normal direction, multiplied with the delta I opening along the normal direction, this is a normal component of this opening vector, divided by 2. So because this is a elastic unloading, you can consider that the opening up as elastic unloading, and F changes linearly from F1 to 0 when it's opened up. And you divide this by dA, which is the area of your crack. So we assume that through the thickness, we have a unit thickness, which is the thickness of 1. So this is the energy release rate along the mode 1 direction. Similarly, we have the energy release rate along the mode 2 direction. And these two energy release rates can be plugged into a certain failure criteria. For instance, this power law criteria. And N would correspond to mode 1, and S or T would correspond to mode 2. So this is a two-dimensional problem, so we only have two components, maybe let's say the first two. When this criteria is satisfied, we say that fracture is going to happen, and then we simply release so there will be a double node, and we simply release the node, and then create the opening, and then let the crack propagate forward. Typically, dA would be the length of an element ahead of the crack tip, and so within this region you have elements of a similar length. And this is a very popular approach when you know where the crack is going to propagate, and when you have a pre-crack existing in the model. So it's an alternative to cohesive element. It's more computationally efficient than cohesive element when used correctly, but it's more restrictive than cohesive element also. So when you have a well-defined debounding problem, then this technique can be useful. But otherwise, if you don't know where the crack is going to appear, if you don't have a pre-crack existing in the model, then the smear crack or cohesive elements are preferred choices. So this is the little extra I would like to show you.